Yeah, so we are at this point, elimination method. Yeah. So last time at the end, I said, as soon as we find some elements that are not relevant, we should remove them immediately from the, data processing. Yeah. In that way, we can avoid redundant comparisons. Yeah. All right. Yeah. Now, in this example, so let me show you how do we apply this elimination method to solve this problem. Yeah. Notation. Yeah. Because sometimes, in order to express our thinking in a concise way, we want to use some special expressions, special notations. Yeah. For example, for comparison, yeah, although we can write sentences, words, yeah, but notation, we can represent our ideas quickly. Yeah. All right. For example, we compare two elements, and we want to get the winner. Yeah. So after this comparison, yeah, so we use this very concise notation to tell us we have a winner. Okay? Yeah. For the winner, sometimes we mean the smaller one, sometimes we mean the larger one, right? Yeah. Based on the criteria. Yeah. If our goal finding a minimum, then the smaller number will be the winner. If we need to find the maximum, then the larger number will be the winner. Yeah. Yeah. All right. Yeah. So now, let us work on our current data. Yeah. It's an array, yeah, with n distinct elements. Yeah. All right. The first step, when we do the data processing, yeah, we need to take a special step. Yeah. In problem solving, it is very common, this step. Yeah. So that's called, so we know we organize the data, right? The question, how to organize data. Yeah. Organizing data, that's a very high level general description. Yeah. But we want to get some concrete details. Yeah. What do we mean? In which way you organize your data? Yeah. Here, we use the special way. Group the data in pairs. Yeah. So that's a special way. Yeah. Group the data. Group the elements. Yeah. Here, elements in pairs. Yeah. Because in this way, it is more friendly for data comparisons. Yeah. When you group all your elements in pairs, you can make comparisons easily, right? Yeah. So we prepare the environment for comparisons. All right. Yeah. The first two elements, that's our first pair, in a group. Yeah. Second pair, and so on. Yeah. Then we try to group all the elements, but there is some small question we need to answer. Yeah. Because we may not be able to group or pair all the elements. Right? Yeah. So we need to look at the number of elements. If this number is an even number or odd number. Yeah. If it is an even number, then we can group all the elements in pairs. If it is an odd number, then we cannot, right? The last element cannot be paired. Yeah. So here I want to talk about a general strategy in problem solving. Yeah. When we have a few cases to consider in general problem solving, yeah, we always work on the simplest case first. Yeah. It's very simple, very natural, right? Yeah. But it's very important. Here we have two cases, the even case and the odd case. Now we need to pick the easier one. Yeah. We want to work on the easier case first. Yeah. So it's very easy to see the even case is easier, right? Yeah. Because all the pairs, all the elements are grouped in pairs. Yeah. So now we apply some commonly used method here. Yeah. Tournament method. Yeah. Yeah. So tournament method, we group the elements in pairs and we play round by round, first round, second round, and the third round. Yeah. So the simple arrangement. Yeah. Yeah. So let's work on our current array. Yeah. The data size n in our first case study, yeah, we assume n is an even number. Yeah. So here, yeah, we pick the even case to work. After that, after we solve the problem for the even case, then we work on the odd case after that. Because at that time, we have built up some experience. We will have better understanding on our data, on our problem. Then we can do better. Yeah. So that's the rationale behind our strategy, the simple strategy. Yeah. All right. Yeah. For the even case, now the first round. Yeah. First round, yeah. First group, we need to make our first comparison. Okay. All right. But when we make the first comparison, we have two possible outcomes, right? Yeah. X1 could be the winner or X2 could be the winner. Yeah. Then the second group, X3, X4, yeah, we apply another comparison and also two possible outcomes, yeah, and so on. Yeah. So let's keep doing comparisons like this, and the last comparison between these last two elements. Now we need to look at the first round comparison results. What kind of result can we get after the first round comparisons? Yeah. We need to look at the winners, right? Yeah. Winners, eliminations. We need to look at that part. All right. In the first comparison, yeah, there are two cases, right? Yeah. X1 could be the winner, X2 could be the winner. Two cases. Similarly, for each of the remaining pairs of elements, we have two cases. Yeah. Then, first thing, how many total cases do we have? Yeah. Yeah. Yeah? Because we need to cover all the possible cases, right? In our problem solving, we don't want to miss any cases. Yeah. We want to cover all the cases in our problem solving. So the first thing we want to know, how many total cases in our first round comparisons. Yeah. So here we can do some simple calculation. Yeah. Here, this is the situation, counting situation, right? Yeah, this is a typical, basic counting situation. In this situation, there is a simple method used in counting called a product rule. Product rule. So we need to calculate product of all these numbers. Yeah. So each pair too. Yeah. So when we look at all the pairs, the total number of cases should be the product of all these numbers. Yeah. So in counting, we apply the product rule or law. Yeah. Yeah. All right. Yeah. So then the result should be 2 to the n over 2. This number. Yeah. After we apply the product rule. Yeah. 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 So in counting, yeah, here in your discrete math, yeah, you learn some basic counting methods. Yeah. So there are 2 basic cases. One, you need to use sum rule or sum law. Yeah. So another is the product rule, or sometimes law. All right. Sum. Yeah. Here, let me give you an example for this. Yeah. Under what situation people need to apply, sum rule. All right. For example, from A, you go to from A to B. Yeah. So then from B to C. Yeah. So here. All right. Yeah, so yeah, I should write this way. So our goal, we want to go from A to B, right? Yeah. Yeah. From A to B, if we take, airplane, yeah. For example, if we take airplane, we have 3 different ways. Yeah. So this is, by air. Okay. 3 different ways. Then, if we take, ground transportation, the ground, okay, all right, two ways. Then the total, we need to use sum rule, okay, or sum law. Yeah. But product case, yeah. Now we go from A to B, but in the middle there is a C city. We have to stop by C city. All right. Yeah. So then, from A to C, there are 3 ways. All right. From C to B, there are 2 ways. Yeah. So in this case, how many ways from A to B? Yeah. So that's the product rule. Okay. All right. So in our current situation, we should apply the product law. Yeah. So you get this number. But this number is too big, right? Yeah. Yeah. This many cases you can think about. Yeah. When n is a relatively large number, it's huge, right? Think about if we have 100 elements. Yeah. So then this number, you need to consider 2 to the 50th power. So this huge number, Nobody can handle this many cases, right? Yeah. Yeah. So in our discussion, yeah, in this situation, yeah, so when we work on our general computing problems, we need to deal with this common question quite a lot. Yeah. Here I want to explain the easiest way for us in this situation. Yeah. So the easiest way in this situation, we pick a representative. In this situation, we pick a representative to work on. Okay? All right. So one case can represent all the other cases. If we can observe this kind of representation, then we only need to work on one case. Yeah. Here we have the situation. Here we only need to work on one special case. Yeah. Because all the other cases, they are very similar to this representative case. Yeah. All right. For example, in the first pair, x1 is the winner or x2 is the winner. Are they similar? Right? Yeah. They're similar. Yeah. Okay? Yeah? So x1 is the winner, x2 winner. So you can see either one is the winner. Yeah. They are symmetric. These two cases are symmetric. If we flip, for example, if we switch x1 and x2, we jump to the other case, right? Yeah. So when we see this kind of symmetry, we can take advantage of the symmetry. So we only need to pick one of the two subcases by using the symmetry property here. All right? Yeah. Similarly, for second pair, there is another symmetry between x3 and x4, right? Yeah. So for each comparison, symmetric, we can, based on the symmetry property, we only need to pick one of the two cases. Yeah. Then when you do the product, yeah, because each comparison, we can pick one of the two winners, right? Yeah. So at the end, yeah, we just pick convenient winners for all these pairs. Yeah. So here I pick x1 the winner for the first pair. The second pair I pick x3 the winner, yeah, and so on. Right? Yeah. In this way, although we only get a special case, but can you see the special case is good enough to represent all the other cases? Yeah, by symmetry, right? Yeah. If you can show in this special case you can solve the problem, then when you move to any of the other remaining cases, you can do the same thing to solve the problem, right? Yeah. So that's the reason. Yeah. Yeah. We just repeat the same work, right? Yeah, same work. Yeah. Yeah. So we do not need to go through all the different cases, right? Yeah. So that's the idea. Yeah. So here, yeah, in this way, we only consider one case. Yeah. All right. Representative case. Yeah. All right. Yeah. So here I may like to point out one typical way our students do in problem solving. Yeah. So when I did a grading before, yeah, I noticed many students, they try to, in this situation, so they try to provide some complete discussion. Yeah, so they want to cover all the cases, but nobody can exhaust all the cases. Yeah, so everybody can see it. Yeah, so those students, they use this way. Yeah, so let me point it out. Yeah, for example, they compare x1, x2. Yeah, so then you need to have a winner, right? Yeah, have a winner. So which one should be the winner? Yeah, x1 could be winner, x2 could be winner. There are two possibilities, right? But they do not want to discuss these two cases separately because it's not efficient. Yeah. So they want to discuss once, yeah, but they didn't use our representative way. Yeah. Yeah. We use the representative way. So they use this way. They introduce a new notation for the winner. Yeah. For example, yeah, they don't want to use x1, the winner. They don't want to use x2, the winner. So they introduce a new notation, A. Yeah. So this place, they use a new variable. New variable. Yeah. All right. Yeah. Then, because there is another comparison, so this one, they introduce another new variable B. Yeah. To separate, right? Yeah. Also, they need to work on only one case, yeah, but use a different variable. Yeah. Here I want to say this method, although logically correct, but not as good as our representative way. Why? Because you may use too many variables. You introduce too many new variables. Right? You can think, yeah. Because sometimes we may need to work on 8 elements, 9 elements. Think about how many new variables you need to use. Yeah. Then it's quite messy. The discussion quite messy. Because when you have so many variables, it's hard to keep track of those variables, right? You need to keep track of the variable. When you see A, you want to connect to the original elements. Yeah, so it is the winner from the comparison of x1, x2. When you see D, you need to make connection. But it's hard to keep track of your data, right? Yeah. So that way is not a good way. Yeah. So I don't want to encourage that way. So that way, the problem, yeah, so here, so when you write your solutions, try to avoid that problem, because the problem is the readability. The readability of your solution is not good. Because when I try to understand your solution, it's very hard. I need to draw diagrams to keep track of the relationship. Yeah. So very hard. For you, when you do your work, you also need to keep track of your relationships, right? Yeah. It's very hard. Yeah. Our representative way, that's the best. We do not introduce new variables. We still use our existing variables, but you can make connection quickly, right? Because you see your x1, you see your x3. Yeah? So that's the direct way. Yeah, not indirect way. We see A, you see B, indirect way. Yeah. Here, I just make some comments. Yeah. All right. Then, yeah, so in my diagram, yeah, so now we move to the next round. Yeah, yeah. So here I already covered, all these things. So let's do some cleanup work. Yeah, cleanup. Yeah, yeah. This is our current state after first round comparisons. All right. Then, yeah, sometimes we want to represent the state of our data visually, in a visual way. Yeah. So here, I like to use this, vertical bar connecting these two elements. The upper one is the winner. The lower one is the loser, and so on. In this way, when I see this diagram, I know the meaning. Because I do not want to write too many sentences, right? Although we can write a lot of sentences, but you need to read, you need to understand. It takes a lot of time, right? If we draw diagrams, we can save a lot of writing, understanding, connections, a lot of time. All right, so for second comparison, we get this result. The last comparison, we get this result. All right. Then, next round. What should we do next round? This time, we need to apply elimination method. We need to do some analysis. Then we apply this elimination method. So you need to make observation to discover some nice properties before you can do elimination. So here, let's do some observation work. All right. So in data grouping, so there is one common way people do, put the like elements in the same group. Put the like elements. The elements with same situations. So those elements in the same group. Because they share same properties. So we want to do that kind of natural characterization. All right. Here, all the winners, we want to put them in the same group. So they share same properties because they are all winners in the first round. So that's the common data processing manipulation work we use. Similarly, all the losers, we put them in another group. So the losers group. Because they share the same property. Then we apply their common properties to do the elimination on these two groups. Winners group and a losers group. So that's the first step. Second step, then we need to make our critical observation. We need to make some very important observations here. All right. So what kind of observation? Remember, our goal, we need to remember our goal. We need to find a maximum and a minimum, right? That's our goal. Now you need to connect your maximum, minimum to your current data state. All right. When you look at the maximum, can you see the maximum can only appear in the winners group? The maximum cannot appear in the losers group, right? It's very easy to see it. Similarly, the minimum can only appear in the losers group. The minimum cannot appear in the winners group. Then you can apply the elimination method. Because when you look for the maximum, you only need to work on the elements in the winners group. And then when you do the work, you eliminate the whole losers group. Yeah. Similarly, when you look for the minimum, you can eliminate the whole winners group. That's quite a lot, elimination. Yeah. So that's the critical observation. This step is the critical observation. Yeah. After you can see this basic fact, yeah, the next round, it is much easier. Yeah. All right. Yeah. Yeah. All right. So now, yeah, so we summarize these two properties. Yeah. Yeah. So now let's move to the next round. Yeah, elimination. Yeah. 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 All right. Yeah. So the next round, yeah, then we can apply. Yeah. We can apply the results we did from our last class to do the counting. Okay? We need to count the total number of comparisons. Yeah. In the first round, we did this many comparisons, n over 2. Yeah. This many pairs. So each pair, one comparison. So this many comparisons. Then the second round. So this is the second round. Okay? Yeah. Second round. In the second round, in the winners group, we need to find the maximum. Then we apply the solution of our finding the minimum, right? Yeah. So, you know, we generalize our previous solution a little bit. Finding the minimum, we generalize it to the maximum case. Yeah. So we need total number of elements minus 1. Yeah. The result. Yeah. N over 2 minus 1. Yeah. Similarly, for the minimum, we need also n over 2 minus 1. Okay? Yeah. So we get our solution. Yeah. Both maximum and the minimum when n is even here. Yeah. Here, let's calculate the total. Total number of comparisons, yeah, 3n over 2 minus 2. Yeah. The final answer. Okay? Yeah. Yeah. So we solve this problem, but only for the even case. Yeah. For the odd case, we need to modify this even case slightly. Yeah. The main idea is similar, yeah, but you need to deal with the singleton. Yeah. Because the first round, there is one element that cannot be paired. So there is a special small problem you need to handle, that singleton problem. Yeah. All right. Yeah. Now for the other case. Yeah. So our main focus is on this singleton element. Yeah. Xn. Xn, yeah, cannot be paired. So in our first round comparison, we cannot cover Xn. Yeah. Yeah. No comparison regarding the last element. Yeah. All right. Now when we move to the second round, yeah, we need to define winners group and a losers group, right? Yeah. But this time, our definitions of winners group and the losers group should be modified. In particular, on this singleton element. Yeah. How do we define winners group? Yeah. So let's see. Yeah. So yeah, here the strategy. Yeah. So here I want to. So the strategy, because there is a gap, right? There is a gap between even case and odd case. Yeah. But when we work on the odd case, we don't want to start from scratch, right? Yeah. Because that's too slow. So we want to work on the difference part between these two cases. Yeah. So that's the gap part. Yeah. So for that part, that's the singleton place. That's the gap part. Yeah. All right. Now we define winners group. Yeah. Yeah. So we circle those winners and the losers, but how do we assign xn? Yeah. Because we need to assign xn to at least one of the two groups, right? Yeah. We cannot leave this element out. Yeah. But then when we assign xn, does it belong to the winners group or the losers group? Yeah. So we need to be very careful. Yeah. We have no information to make the decision, right? Yeah. No information to tell us xn should belong to the winners group or the losers group. Okay? In other words, both cases are possible. Yeah. So xn could be in the winners group. It could also be in the losers group. So in that situation, we assign this element to both groups. Okay? Yeah? Yeah. Both groups. Yeah. It belongs to the winners group. Yeah. It also belongs to the losers group. Yeah. All right? Yeah. So winners group, yeah, we need to include, cover xn. Losers group, yeah, we also need to cover it. Right? Yeah. Yeah. So that's our modification part. That's the gap part, the work we do for the gap part. All right. Then next round, we can do the counting. Yeah. The first round, the number comparisons, n minus 1 over 2. Yeah, because we take out the last element. Yeah. Then second round, the winners group. Yeah. So when we calculate the total number of comparisons, we apply our, finding the minimum, the solution of finding the minimum. Yeah. The total number of elements n over 2 plus 1, right? Yeah, because it includes the last element, so we plus 1, then minus 1, right? Yeah, because our solution is the total number of elements minus 1. Yeah, so then plus 1 minus 1 cancel out. Yeah, yeah, total number of elements n minus 1 over 2. Yeah, so that's why this number. Okay, yeah, n minus 1 over 2. Then for the minimum, yeah, we have this number. Then adding together the total, yeah. So that is the representation for the other case. For the other case. Okay? Yeah. All right. Yeah. So we solve this problem. We solve this problem. Okay? Yeah. So look at it. For the even case, yeah. So yeah, let me see. Yeah. The last thing we need to do, unify the two formulas. Yeah. Because for the even case, for the odd case, there are two different formulas, right? The forms are different. For the even case, the formula is 3m over 2 minus 2. For the odd case, 3 times n minus 1 over 2. Yeah, they're quite different. Yeah. All right. And when we apply the solutions of this question, we always need to consider these two cases, right? Yeah. We always need to memorize these two formulas, right? Yeah. So that's not very convenient. Yeah. So we like to unify these two formulas. Yeah. We want to find one formula that covers both formulas. Yeah, one formula. Yeah. It works for both cases. Yeah. All right. So now let's see how to do it. Yeah. So here, okay, we need to find the common part. Yeah. So they have difference part, they have common part. Common part, look at 3n over 2. This one also, it has the 3n over 2, right? Yeah. The difference part minus part, slightly different. Yeah. So here, our strategy, we compare the similarities between these two formulas. Yeah. So we want to keep the similar part. Yeah. For the difference part, we want to find a nice way to cover the difference part. Yeah. All right. Yeah. Here, yeah, the similar part. Yeah. Yeah. So let's compare these two formulas. Yeah. All right. Yeah. The two formulas. Yeah, because the first formula there is a minus 2. So second formula we also want to, try to all get minus 2. Yeah. Because we want to use the same pattern. Between these two formulas, we want to use the same structure. Yeah. Yeah. The minus 2, that's part of the structure we want to keep. Yeah. All right. After we make that part, we need to add 2. Yeah. So now let's simplify it. Yeah. After that, so we have this representation. Yeah. Now let's compare the difference part. Yeah. Minus 2 part, they match. Yeah. But this part, slightly different. So we need to find a way to cover both cases. Yeah. Yeah. The case is, yeah, here. Result, the case is, yeah. For this expression, when n is even, 3n over 2, it is an integer, right? Yeah. For this case, when n is an odd number, 3n plus 1 is over 2 is an integer. Yeah. 3n plus 1. Yeah. 3n is odd number, right? 3n plus 1, it becomes even number over 2, it is an integer. Yeah. Here you can see the reason. For even case, we use 3n. For odd case, we use 3n plus 1. Here you can see the reason is people want to adjust to make it divisible by 2. In other words, to make the numerator an even number, right? Yeah. So we make adjustment to make numerator an even number. Yeah. And to make the fraction an integer, right? Yeah. So to make the fraction integer, so we use here ceiling function. Yeah. Because plus 1, we round it up, right? 3n over 2. Yeah. For other case, 3n over 2 is not an integer. Then we round it up to make it an integer. So plus 1, we rounded 3n over 2 up to make it integer. Yeah. So our final formula here, yeah, so here, after the discussion, the final formula, yeah, we rounded it up. So we take 3n over 2. Sometimes it's integer, sometimes it's not an integer, but if it is not an integer, we take the ceiling function on it to round it up. Okay? Yeah. So then the final formula, the unified final formula is this, 3n over 2. Ceiling function, then minus 2. Yeah. Yeah. So this method, although it's a simple example here, yeah, but this situation quite common. Yeah. So sometimes we may have 2 cases, typically 2 cases. Yeah. But people want to use one formula to cover those 2 cases. Yeah. Because it's more convenient. Yeah. So we only need to carry one formula everywhere when we need to apply the solution of this problem. Yeah. All right. Yeah. Then the last thing, yeah, before I finish this part, the last thing I want to mention, yeah. Remember the topic of this part, part D, optimality, right? Yeah. I want to give you the result about optimality. So for this question, yeah, this formula is optimal. Although it's very hard to prove, yeah, but there is a proof for it. Yeah. So here I just give you the result. Yeah. It is optimal. Yeah. This formula gives us the optimal solution. So nobody can improve it. Yeah. That's the best people can do. Yeah. Finding both the maximum and the minimum. Yeah. This formula gives you the best solution. Yeah. All right, so we complete this topic. Yeah. All right. Next, yeah. So let's move to new module, module 2, new topic. Yeah. Let me get out of this presentation and switch to new file. All right. Okay. Yeah. All right. Yeah. Part A. Changing my pen color. Yeah. All right. Yeah. Module 2, the title, Analysis of Algorithm Efficiencies and the Brute Force Method. Yeah. Brute Force Method, we use it before. Yeah. Here just, try to give another round understanding. Yeah. Part A, problem solving from experience and elimination method. Yeah, so we practice more on this elimination method. Yeah. 8.1, selection sort. Yeah. That's the first sort in this class. In this class, we will learn many about 6 sorts. Yeah, so this is the first one, yeah. Selection sort. Yeah. All right. So let's look at the problem. Yeah. Number 6, sort an array. Yeah. The question, very simple. Yeah. Given an array, yeah. General array, yeah. How to sort it in ascending order. So in this computing problem, basic computing problem, when we solve this problem, I want to explain a very basic and a general way people use to solve computing problems. That is, apply your experience. Yeah. Very natural way, yeah. Because you need to have some experience, right? Yeah. You need to have some background. You need to have some experience. Yeah. If you have a lot of experience, then you can do better. Yeah. So you will be a stronger problem solver if you have a lot of experience. Yeah. Yeah. So for this class, we need to build up our experience. Yeah. Currently, the knowledge we have learned in Module 1, that's our experience. Yeah. We just complete Module 1. Yeah. So that's our experience. So we need to use the knowledge we have learned in Module 1 to solve this current problem. Yeah. All right. Let's look at the analysis part. Yeah. Problem type, sort type, right? Yeah. So remember 3 basic types of problems in this class. Yeah. Search, sort, and the selection. 3 types. Yeah. So this is the sort type. Yeah. I also give you the reference sections. Yeah. All right. Let's do analysis. Yeah. So when we solve a problem, so I want to go through the whole thinking process in problem solving. Yeah. Try to give you the training in problem solving. Yeah. All right. Find a solution from our experience from Module 1. Yeah. Yeah. All right. Explore properties. Yeah. So we need to understand our current environment. Yeah. And we need to observe the properties from our data, the given data. Yeah. But when we explore the properties, there are many ways to view our data. Yeah. So later I will talk about different views to understand our data. Yeah. All right. Yeah. So these 2 points. So that's the basic guidelines for our problem solvers. All right. Now we apply another commonly used method in problem solving, backward thinking. Yeah. So actually many people use that way. Yeah. Backward thinking. Yeah. So pretty straightforward. Yeah. So we imagine when the array is sorted already, yeah, what property can we discover? Yeah. So we do the logical deductions from the end. Yeah. When we reach the end of the solution, yeah, at the end of the solution, the array is sorted, right? That's the end. Yeah. Then we want to see what property we can discover in this situation. Yeah. Here, we assume distinct elements. In the original question, we do not have that assumption. Yeah. Don't worry. I explained last time. Don't worry. Even original problem, we don't have this assumption. Yeah. But we can still make it. Why? Even if the original, we can still add this assumption for convenience. Yeah, definitely. Our discussion will be much simpler, right? Yeah. So it's better for our initial solution, right? Yeah. So why we can do that? Because this is our first round, right? Yeah. If people ask you why you can make that assumption, yeah, you just tell them, I use this assumption as my first round solution. Okay? Yeah, part of the solution, right? After I complete it, then I go back to the original problem. Yeah, I remove this assumption, so I can work on the original problem as my second round, right? Yeah. You cannot say you cannot use multiple rounds. Yeah, nobody can tell you cannot use multiple rounds. Yeah, it's very natural. People solve a problem using multiple rounds. Yeah. All right. Yeah. So we can use this assumption comfortably. Yeah. All right. How to connect this problem to the minimum problem? Yeah. Here you can see if we recall the experience in Module 1, the most relevant experience is the minimum problem. Yeah? Linear search, it looks irrelevant, right? Yeah, because it's a search problem. Irrelevant. Yeah. Evaluate polynomials, that experience, although it's a good experience, but irrelevant to this current problem, yeah, and so on. Yeah. You can see the most likely relevant experience is this problem. Yeah. So let us try to make connection. We need to connect the dots, right? Yeah. So we have experience, but you need to make connection so that you can apply your old experience. Yeah. First, in our analysis, we need to establish the connection between our old problem and this new problem. Yeah. Let's do this part. Yeah. Do some observation. We use simple diagram to help us understand the data. Yeah. Now, yeah, because we make the end point of the solution as the starting point. Yeah. We assume the array is sorted. That's the end point. But in our backward thinking, that's our starting point, right? Yeah. So here you can see the array has been sorted. Yeah. So it is in ascending order already. Yeah. Now, look at the data. What property can you see? Yeah. Just view your data. Yeah. But when you answer this question, now remember, we want to make connection. We want to connect to, finding the minimum problem. So you need to connect to the minimum. Yeah. Connect to the minimum. Make that connection. Okay? Yeah. You can see the first element in this sorted array must be the minimum, right? Yeah. Yeah. So that's our initial observation. First, let me write down. First element in the sorted array is the minimum. That's our initial observation. Okay? All right. Then, so this is the basic fact we have observed. Basic fact we have observed. Right? Then, next step, we need to move one step forward. So we cannot stay here. We cannot stay in the same place. We need to move forward. Okay? Yeah. One step forward. Yeah. All right. Based on this fact, yeah, we want to adjust our view slightly. Yeah. So in your understanding, you need to, when you want to make a progress, you need to do a lot of manipulations on your data. Okay? Yeah. So if you stay in the same place, you never do anything different. So you cannot move forward. So here we need to do something different. Yeah. Transformation. So we call it transformation. Yeah. We need to do data transformations. Yeah. All right. So here, the same fact, yeah, but I want to rewrite this fact in a different way. That's the transformation, right? So in our mind, yeah, in our thinking, we do transformations on our data. Yeah. All right. So our transformation is like this. The minimum must be the first element in the sorted array. How about that? That's transformation, right? Same thing. Yeah, so here you can see, basically, the second statement is the same as the first statement, right? Yeah, but you can, yeah, so you try to feel about the difference. Yeah. Although second statement essentially the same as the first statement, but the second statement gives us a different view on our data. That's important. Yeah. Although we do not change the fact from the first statement, but we change the view of our data on the second statement. Yeah, the view is different. The view is, why the view is different? Yeah. Because the view of the first statement, you sort this array first, right? Then you identify the first element is minimum. Yeah? So in that order. But the second statement changes the order. Yeah. You find the minimum first, all right? After you find the minimum, then you connect. Yeah. So this minimum must be the first element in the sorted array. Yeah. So that order, that viewpoint is different. That's important. Yeah. So that's our progress. All right. Yeah. So with this second statement in our observation, now we can make some progress. Yeah. Because we need to find the minimum first, right? Yeah. When you find the minimum, do you apply our existing solution? Finding the minimum. Yeah, we have existing solution. We apply it. We can find the minimum. All right. After you apply that solution, yeah, you'll find the minimum. Then you'll know that minimum must be the first element in the final sorted array. Yeah. So you have the first element in your destination array. You find the first element in your destination array. That's your progress, right? That's one step forward. Yeah, think about that. Think about that analysis. Yeah. Okay. Yeah. Yeah. All right. So that observation is important. It's critical for this for the solution. All right. Yeah. So then A0. How to get A0? Yeah. Just find the minimum of the original array. That's simple. You get the first element in your destination array. Okay? All right? Yeah. After we complete it, then the second step. Yeah? So you need to, find all the remaining elements in the destination array, right? Yeah. So after you find the first element in the destination array, then you need to find second element in the destination array, right? Yeah. The question, how to get second element in the destination array? Yeah. Then, here I introduce a useful concept in this situation. It's called in place. Yeah. The element is in place. Yeah. So this in place, in this situation, we talk about element in place. Yeah. Because in our later part, we will learn another meaning of in place. So that's not element in place, that's the algorithm in place. Yeah. Two different meanings. All right. It's pretty straightforward for element in place. Yeah. Because when you get some element in the right location of the destination array, we call it in place. Yeah. So this A0, after we find the minimum, we know it must be in the first position of the sorted array. So this element we call it is in place. Yeah. It is in its right position in the destination array. Yeah. Yeah. All right. Yeah. So because when we use this concept, yeah, so it's very easy. Yeah, in our discussion, we can save a lot of words. Yeah, we can save a lot of words. Yeah. All right. Then, yeah, next round we can apply elimination method. Yeah, because after we find that the first element is in place, then we do not need to touch it anymore, right? Yeah, because we already put it in place, then we can leave it there. We never need to touch it anymore, right? Yeah. Yeah. If we do not need to touch it anymore, we should eliminate it from our data processing, right? Yeah. Yeah. So for that reason, we apply this elimination method. We remove X0 for our data processing. Yeah. All right. Then we look at the remaining elements. Then A1, similarly, A1 must be the minimum of the current array. The current array excludes A0. Yeah. We eliminate it. So no A0 anymore to be considered. Yeah. Yeah. So the next round, we put A1 in place. After we apply the existing solution for our finding the minimum problem, we find another, the second element in place, A1 in place, and so on. Yeah. Every time we apply the solution of this minimum problem, we put one more element in place. How about that? At the end, we put all elements in place, right? Yeah. If we repeat this process round by round, at the end, you can see we put all elements in place. How about that? Okay? Yeah. So that idea, pretty straightforward. Yeah. All right. So then, we complete the solution, right? Yeah, you can see in this analysis, we complete the sorting task. Yeah, so we get a solution for our first sort in this class. Yeah. All right. Then we also need to do analysis. Yeah. Yeah. How to make all elements in place. Yeah. Yeah. Here, I just do a summary. Okay. Yeah. All right. So here, let me describe. The first round, yeah, we put the first element in place by a certain number of comparisons. Second round, second element in place by a certain number of comparisons, and so on. Okay, one by one. At the end, yeah, because when we have only one element left in the last step, we do not need to do any comparison. Yeah, because only one position left. Yeah, yeah, no comparison, we can put it in place immediately. Yeah. So based on this view, yeah, we can calculate. Yeah, we can. Yeah. So here, yeah. So this simple fact. Yeah, all elements, when all elements are in place, so the array must be sorted. Yeah. All right. Then let's count number of comparisons. Okay. Yeah. All right. First round, second round, yeah. First round, how many? Yeah. First round, yeah. We need to find a minimum among total n elements. So based on the known solution of that, finding the minimum n minus 1. Yeah. But second round, because after elimination, we have one element fewer. We have one fewer number of elements. So the second round, we need to add n minus 2 and so on. Yeah. Then, yeah. We need to add up consecutive integers from 1 through n minus 1. So then we apply our summation formula. So we get 1/2 times n times n minus 1. Okay? Yeah. All right. Yeah. Yeah. So let me, complete the conclusion before our break time. Yeah. So we know this total number of comparisons, this formula. Yeah. In our efficiency analysis, we need to look at the best case, worst case, and average case, right? Yeah. We have 3 different types of efficiencies. Yeah. So now we want to look at the answers for those 3 different types of efficiencies. Yeah. First, what's the best case efficiency? Yeah. The best case efficiency. Yeah. Look at our data. Yeah. The data processing details. Yeah. Recall a little bit. What's the best case efficiency? Okay, all right. Answer is very simple. The best case, worst case, average case. Yeah. Because when you look at the whole process, you will see you only have one case. No matter what inputs you have, what orders for your data you have, no matter what, you always do the same thing. Because finding the minimum, you always need to use the same number of comparisons no matter what. No matter what orders you have. Yeah. Yeah. So for that observation, your conclusion is this formula belongs to all these 3 cases. Best case is this formula, worst case is this formula, average case is also this formula. Okay? Yeah. So that's the final conclusion. Yeah. All right. So we're at a break time. So let me stop right here and take a 10-minute break.